Ariel, named after a spirit of the air, orbits Uranus at a distance of about 190,000 kilometers. It's the fourth largest of Uranus's moons, but it's still pretty small compared to Earth's moon. Imagine a sphere with a diameter roughly half that of our moon, its surface scarred by eons of cosmic collisions. This is Ariel, a world locked in a perpetual dance around its icy giant parent. Ariel's orbit is a testament to the powerful gravitational forces at play within the Uranian system. It is tidally locked to Uranus, meaning that the same side of Ariel always faces the planet. This gravitational embrace has profound implications for Ariel's geology and evolution, shaping its surface and influencing its internal structure. But Ariel is not alone in its celestial waltz. It shares its orbital neighborhood with other moons, each vying for gravitational dominance. This delicate balance of forces creates a complex and ever-changing environment where even the slightest nudge can have dramatic consequences over astronomical timescales. The Uranian system, with its tilted axis and retinue of moons, presents a unique challenge for astronomers seeking to understand its formation and evolution. The moons of Uranus, including Ariel, hold vital clues that can help us piece together the history of this enigmatic planetary system. Their composition, their orbits, and their surface features all provide valuable data points in our quest to unravel the mysteries of the outer solar system. Ariel's story is intimately intertwined with the story of Uranus itself. The formation of this giant planet, tilted on its side, remains one of the enduring mysteries of our solar system. Some scientists believe that a cataclysmic collision early in its history may have knocked Uranus off its axis, scattering debris that eventually coalesced into its moons. If we could turn back the cosmic clock and witness the birth of the Uranian system, we might see a chaotic scene of swirling gas and dust, punctuated by the fiery trails of planetesimals colliding and merging. Out of this cosmic maelstrom, Uranus emerged, its gravitational pull drawing in the remaining debris to form its rings and moons. Ariel, like the other Uranian moons, bears witness to this ancient drama. Its surface, a tapestry of craters, canyons, and vast plains, tells a tale of intense bombardment and geological upheaval. Each scar, each ridge, and each smooth expanse holds clues to the processes that shaped this distant world. As we delve deeper into the mysteries of Ariel, we are reminded that our solar system is a place of constant change and evolution. The planets and moons we observe today are not static entities, but dynamic worlds shaped by forces that have been at play for billions of years. And so, our exploration of Ariel becomes more than just a journey to a distant moon. It becomes a journey through time, a quest to understand the very origins of our cosmic neighborhood. Imagine gazing upon Ariel from a distant spacecraft, the pale light of the distant sun illuminating its icy surface. Ariel, a world frozen in time, a silent sentinel orbiting its giant planet. Its surface, a canvas of water ice and rock, hints at a dynamic history. Ariel's nearly spherical shape, shaped by its own gravity, distinguishes it from smaller moons. Ariel's orbit around Uranus, a delicate balance of gravitational forces, a challenging target for spacecraft. Ariel's surface bears witness to a long and tumultuous history, etched with the scars of countless impacts from asteroids, comets, and other celestial debris. These impact craters, ranging in size from small, bowl-shaped depressions to vast, multi-ringed basins, provide a record of the bombardment that has shaped the outer solar system for billions of years. One of the most striking features on Ariel's surface is a vast impact basin known as Yangor crater. This colossal crater, spanning over 70 kilometers in diameter, is a testament to the destructive power of these cosmic collisions. The impact that created Yangor crater would have released enormous amounts of energy, melting and vaporizing vast quantities of ice and rock, and leaving a lasting mark on Ariel's surface. But Ariel's surface is not just a passive record of past impacts. It also shows signs of internal geological activity, hinting at a more complex and dynamic history than previously imagined. Long, linear features, known as graben, crisscross Ariel's surface, suggesting that tectonic forces have been at work, stretching and pulling apart its icy crust. These graben, some of which extend for hundreds of kilometers, provide tantalizing evidence that Ariel may have experienced a period of intense geological activity early in its history. Scientists believe that these features may have formed as a result of tidal heating, a process by which the gravitational pull of Uranus stretches and squeezes Ariel's interior, generating heat and causing the icy crust to crack and shift. As Ariel orbits Uranus, it participates in a celestial dance of light and shadow, its surface constantly changing in appearance as it moves through different phases. From Earth, we can only observe Ariel as a faint point of light, but spacecraft missions have provided us with breathtaking images that reveal the intricate details of its surface. During a full phase, when Ariel is directly opposite the Sun in its orbit, its surface is fully illuminated, revealing the full extent of its craters, canyons, and plains. As Ariel moves into its crescent phase, long shadows are cast across its surface, highlighting the subtle topography and revealing details that might otherwise go unnoticed. These changing patterns of light and shadow create a sense of depth and dimension, transforming Ariel from a flat, two-dimensional image into a world with its own unique geography and character. The interplay of light and shadow also plays an important role in shaping Ariel's surface temperature, with the sunlit side experiencing temperatures as high as -173 degrees Celsius, while the dark side plunges to even colder temperatures. But perhaps the most striking aspect of Ariel's appearance from space is its lack of color. Unlike other icy moons in the solar system, such as Europa and Enceladus, which exhibit a wide range of colors and surface markings, Ariel's surface is remarkably uniform in its grayish-white hues. This suggests that Ariel's surface is relatively young, perhaps resurfaced by geological activity in the recent past. As our spacecraft descends closer to Ariel, we begin to appreciate the sheer scale and complexity of the forces that have shaped this distant world. The surface of Ariel is a tapestry woven from impacts, tectonic upheavals, and whispers of cryovolcanic activity. Here, the forces of nature have sculpted a world of stark beauty and mystery. Imagine standing on the edge of a vast crater, its rim stretching out like a lunar mountain range. The crater floor is a sea of shadows, punctuated by sharp peaks, remnants of a colossal impact. Among the most captivating features on Ariel are its canyons, vast chasms that slice through the moon's icy crust. These canyons, some of which dwarf the Grand Canyon, are shaped by powerful tectonic forces. Imagine soaring above one of these canyons in a futuristic spacecraft. The canyon walls are a tapestry of light and shadow with layers of ice and rock. Landslides frozen in mid-descent scar the canyon walls. The origin of Ariel's canyons is still debated among scientists. Some believe they formed through extensional tectonics, where the moon's crust was stretched and cracked. Others suggest ancient cryovolcanic activity, where eruptions of icy magma carved out these channels. Ariel's canyons offer glimpses into the moon's interior. By studying the canyon walls, scientists hope to learn more about Ariel's crust and mantle. Exploration reveals signs of past activity, hinting at a dynamic history. Smooth plains, resurfaced by cryovolcanic flows, line the canyon floors, suggesting icy eruptions once flowed through these channels. Ariel may harbor cryovolcanoes, icy counterparts to Earth's fiery volcanoes. These would erupt with slushy mixtures of water, ammonia, and other volatiles. Imagine fountains of icy particles shooting kilometers into the sky, creating a shimmering curtain of ice crystals that falls back to the surface. The evidence for cryovolcanism on Ariel is primarily circumstantial, based on smooth plains and possible detection of ammonia hydrates. Cryovolcanic eruptions could bring materials from deep within Ariel's interior, providing scientists with a window into the moon's composition and history. The presence of liquid water would make Ariel a prime target in the search for life. Proving cryovolcanism on Ariel will require further exploration. Future missions with sophisticated instruments will be needed to analyze the surface in greater detail. One of the most enduring mysteries of Ariel is its relatively young surface age. Based on crater counts, scientists estimate that parts of Ariel's surface may be as young as 100 million years old, which is quite young considering the Moon's age of over 4 billion years. This youthful appearance suggests that Ariel has experienced a period of intense geological activity in its recent past, resurfacing large portions of its surface and erasing the impact craters that would have accumulated over billions of years. But what could have driven this episode of resurfacing? One possibility is tidal heating, a process by which the gravitational pull of Uranus stretches and squeezes Ariel's interior, generating heat and causing the icy crust to melt and refreeze. This process is thought to be responsible for the intense geological activity observed on some of the moons of Jupiter and Saturn. Another possibility is that Ariel experienced a period of orbital resonance with one of its neighboring moons in the distant past. Orbital resonance occurs when two or more celestial bodies exert a regular, periodic gravitational influence on each other, often resulting in increased tidal heating and geological activity. Whatever the cause of Ariel's youthful appearance, it is clear that this moon has a complex and dynamic history, one that continues to intrigue and inspire scientists today. Further exploration of Ariel, using both ground-based telescopes and future spacecraft missions, is needed to unravel the secrets of this enigmatic world. Ariel's surface is just the beginning. Beneath the icy veil lies a world shaped over billions of years. Scientists believe Ariel has a differentiated interior, with rock and ice layers, a rocky core surrounded by a thick mantle of water ice. This ice may exist in exotic phases, behaving like a viscous fluid. A subsurface ocean could harbor life, with necessary chemical ingredients and energy sources. Ariel's composition is a mix of rock and ice. Gravitational data helps model its internal structure. Ariel likely has a large rocky core. Imagine a giant pendulum swinging. Its swing reveals mass distribution. Ariel's wobbles reveal internal mass. 60% rock, 40% ice. This mix affects its evolution and potential for life. Ariel's internal heat engine is not solely driven by the slow decay of radioactive elements within its rocky core. The Moon also receives a significant energy boost from the gravitational tug-of-war between Uranus and its other moons. This process, known as tidal heating, plays a crucial role in shaping the internal dynamics of many icy moons in the outer solar system. As Ariel orbits Uranus, it is constantly being stretched and squeezed by the giant planet's gravity. This is because the strength of gravity decreases with distance, so the side of Ariel closest to Uranus experiences a stronger gravitational pull than the side farthest away. This difference in gravitational force creates a tidal bulge, stretching Ariel along the line connecting it to Uranus. However, Ariel's orbit is not perfectly circular. Due to gravitational interactions with its neighboring moons, Ariel's orbit is slightly elliptical, meaning its distance from Uranus varies over time. As Ariel moves closer to Uranus, the tidal forces increase, stretching the Moon further. As it moves farther away, the tidal forces decrease, allowing the Moon to relax back towards a more spherical shape. This constant stretching and squeezing generates friction within Ariel's interior, converting some of the orbital energy into heat. This tidal heating can be particularly intense when a moon is locked in an orbital resonance with another moon, as their gravitational interactions reinforce each other, leading to even greater tidal distortions and internal heating. Radiogenic and tidal heating on Ariel could create a subsurface ocean beneath its icy shell. This ocean, shielded from space radiation, might provide a habitable environment for life. Future missions could confirm this hidden ocean. Ariel, like many outer moons, has a thin, wispy atmosphere, more an exosphere than a blanket of gases. This ethereal veil is a mix of gases from Ariel's icy surface and the surrounding space. Imagine standing on Ariel, enduring the extreme cold. You'd see a faint aurora caused by charged particles from Uranus's magnetosphere. This display shows the constant interplay between Ariel and its surroundings. Ariel, orbiting Uranus, is locked in a perpetual deep freeze. The sun appears as a bright star, providing minimal warmth. Temperatures hover around -213 degrees Celsius. Water ice is as hard as rock, and compounds are frozen solid. Ariel's surface is a frozen landscape, with geological processes at a glacial pace. The extreme cold affects its geology and potential for life. Chemical reactions are slow, and liquid water is not possible. But internal heat may create a subsurface ocean. While Ariel may appear frozen in time, a closer look reveals a complex geological history. Craters, vast plains, and tectonic fractures hint at past cryovolcanic activity. Some craters are crisp, others eroded, suggesting varied surface ages. Smooth plains likely formed through cryovolcanic eruptions. Tectonic features indicate internal heating and geological activity. Ariel is more dynamic and geologically active than it appears. One of the most intriguing questions about Ariel is whether it is geologically active today. While the evidence points to a dynamic past, with episodes of cryovolcanism and tectonic activity, it is unclear whether these processes are still ongoing or if they ceased long ago, leaving behind a world frozen in a state of geological quiescence. Imagine that beneath Ariel's icy shell, hidden from our view, lies a vast ocean of liquid water, kept warm by tidal heating from Uranus and the decay of radioactive elements within its core. Could this hypothetical ocean, if it exists, still be erupting onto the surface today, creating new features and erasing old ones? Could it even harbor the conditions necessary for life as we know it to exist? To answer these questions definitively, we need more data. Future missions to the Uranian system, equipped with sophisticated instruments, could search for subtle signs of ongoing geological activity on Ariel. For example, ice-penetrating radar could be used to probe beneath the surface, searching for evidence of a subsurface ocean or active cryovolcanic plumes. Furthermore, by carefully monitoring Ariel's surface over time, looking for subtle changes in its appearance or the composition of its surface ice, scientists could gain further insights into the processes that continue to shape this enigmatic world. The answers to these questions could have profound implications for our understanding of the outer solar system and the potential for life beyond Earth. A fleeting glance, Voyager 2 at Ariel. In 1986, Voyager 2's brief visit to Ariel revealed a complex and intriguing moon. Its cameras captured canyons, craters, and smooth plains. The data revolutionized our understanding of Ariel's geology and composition. Voyager 2's encounter was a testament to human ingenuity. Distant Eyes, Telescopic Observations. Since Voyager 2's historic encounter, our views of Ariel have been limited to the distant eyes of Earth-based and space-based telescopes. While these observations cannot match the detail provided by a close flyby or orbiter, they have nonetheless provided valuable insights into Ariel's composition, surface changes, and interactions with Uranus's magnetosphere. Imagine peering through a powerful telescope, your eyes straining to make out the faint, distant form of Ariel as it orbits Uranus. Through the shimmering turbulence of Earth's atmosphere, you might catch a glimpse of its subtle surface markings, or witness a rare occultation event where Ariel passes behind Uranus or one of its rings, casting a faint shadow that can be detected by sensitive instruments. One of the most valuable tools for studying Ariel from afar has been the Hubble Space Telescope. Orbiting high above Earth's atmosphere, Hubble can capture images of Ariel with far greater clarity than is possible from the ground. These images have been used to refine our maps of Ariel's surface, track changes in its brightness over time, and study the composition of its icy surface. Ground-based telescopes, while limited by atmospheric distortion, have also played an important role in studying Ariel. By observing Ariel in different wavelengths of light, from visible to infrared, astronomers can study the composition of its surface ice, search for signs of active geological processes, and monitor its interactions with the charged particles that stream from Uranus's magnetosphere. Awaiting discovery, future missions to Uranus and its moons. A dedicated mission to Ariel could map its surface, study its composition, and search for signs of a subsurface ocean. Imagine a spacecraft equipped with ice-penetrating radar, peering beneath Ariel's icy shell. A lander could collect samples and deploy instruments to measure Ariel's environment. There is growing momentum for a mission to Uranus and its moons. An orbiter could reveal the formation and evolution of ice giants and their moons. This mission would require cutting-edge technology and international collaboration. The scientific payoff would be immense, providing unprecedented understanding. Ariel beckons us to return and explore its scientific wonders. Ariel's Siren Song. Ariel, an icy moon orbiting Uranus, holds profound mysteries and stark beauty. Voyager 2 and telescopes reveal a dynamic past, hinting at hidden secrets. Ariel's surface, shaped by impacts and tectonic activity, suggests a vibrant history. The possibility of a subsurface ocean calls us to explore further. Ariel's mysteries remind us of the boundless human spirit and the thrill of exploration.